Hi, so now I'll just quickly go over pointers. And so I think I'll jump around these slides. I just had a quick look at them. And what a pointer is. Now, this is the thing that confuses people. Like a pointer is a memory address. So we have, as you can see in this little chunk here, a pointer allows you to store the address of a variable. You don't store the variable directly. You say, I know where the variable is in memory. So we can do this, for instance, like I should actually, anyway, I'll go to the structure of memory first and then we'll get back to it. And so the thing is that if you have some variable allocated in memory, like here, if you use if you pass a reference to it, that you say, hey man, the memory is here, like the variable is here. If you modify it in functions, like I mentioned before, whatever happens here, like to the stack, you pop it, you go to different function contexts and whatnot, this variable in memory, whatever happens to it has stayed there and it's been modified, right? And this is why why pointers are very important, because they allow you to directly modify variables allocated in memory. So before I go into the next couple of slides, I want to look at memory layout, because understanding how memory is laid out is very important, or it can be very important in using pointers. Now, memory in computers is sequential. Like you sort of logically, as you can imagine, you have memory address 0, memory address 1, memory address 2, 3, 4, 5. But essentially, memory addresses correspond to like chunks of data. And this is also why you talk about 32-bit systems, 64-bit systems, because they can actually manage up to 64-bit addresses, I'm pretty sure. This is something I don't really use, this knowledge I don't use very often. But as you can imagine, this is just memory layout here. And then you have in here, this is your entire program, as you can imagine. You have like memory addresses. Like this is not where it would actually be, but you have 0x00, 0x01, 0x02. And so when you allocate some variable, like we'll say char a, the value is stored in memory. Like, so this is your variable called like variable a char, and its value is stored in here. So like we have code that says char a equals 1. And so your computer will go and it will allocate the value of 1 into memory address 0x01. And so if we take the pointer of it, so we say char, we want a char pointer, and we'll call this PA, so pointer of A, we have to say that we use this dereferencing. And what this means is, hey, we want to store in this variable the memory address of A. And so the ampersand A, this is 0x01, because it's this guy here, right? Now, the thing that confuses people is, think of this as a type. Like this is just purely a data type. And then this is the name, just like normal. And what is stored in that variable, because it's a pointer, is probably a memory address. And it just sort of helps tell the compiler and whatnot that, hey, you can expect here a memory address. So usually it'll be like, 32 bytes long, 64 bytes long, or whatever the size of a pointer is on the system. And using this ampersand, you're saying, I want to store the memory address of this variable. And so that's all it is. It's just inside. And then if you were to then print out A, like print F, and you use I think it's %P, so print the pointer of A, of PA, this would print you out 0x01, or it would probably not print it in hex, but it would print you out like some stuff. It would essentially boil down to printing 1, right? And so that is, hopefully that makes sense, that you then, you just take the data type of like some sort of data type pointer, and they're all pointers on a system should be the same size, like actual in bytes variable, but the char pointer lets the program know that at this address there is a 1 byte size variable. So there's only a single variable here. But where if I had an integer, or let's say even better, like make it more explicit, I had a I had a u int 16 right? So this is a common 16-bit type, B equals 2, right? And so this guy will get allocated in memory. And let's just say, like, because it's 2 bytes, it's going to get allocated here, like over two memory addresses. Like if we're on like a system where a single address is 8 bits. And therefore, if we take the reference of B, where B is being stored in 2 and 3, this would equal 2. But when we have our uint 16 pointer, essentially it's just saying, hey, you can at this memory address expect 2 bytes of data, right? And so that's why there's all these different types of pointers. They all point to memory addresses. So as you can imagine, all memory addresses on the system are the same size, like in actual bits. But essentially, by having different pointing types, you can kind of say what you're expecting to find at that memory address. So that's the memory layout. I'm just going to, because I'll get back to a bit more what these actual separate things work, like what all these different things on here are, but I'll get to that in a second. Clean this up a bit. Now, if we go back up to the other slides, I'll go through this a little bit. Now, because I was saying that memory in a system is sequential, things like this becomes very important when you start looking at things such as like arrays. Now, you can have a char array. So you'll have like a char, we'll call it char array A, and we'll give it a length of 10. Now in our memory, you'll have like 10 addresses. So you'll have, let's say 0 down to like 10 here, or 9 in this case, right? Because we're indexing from 0. Now your entire array is stored here in these 10 addresses because we have a length of 10 and their chars are single bytes. And so when we take a pointer to A, now this is going to hopefully not confuse too many people, because we have to use these brackets, char A, that's the type that it is. But this is, without getting too involved, essentially a char pointer. Therefore, if we just use A is already a pointer because so A points to here. This is A. It points to the memory address. So A should be, if we just use A, it's 0. It is equal to 0 because it's pointing to this top address. Now, in an array, we use this square notation, and the square notation essentially with some index in it, it says return to me A, the memory address of A, plus I times, and then the type, the size of the type. So in this case, A points to the top location. If we put in a 2, it's saying I want you to go 2 times the size of the type, so the chart is 1 byte. So it's saying I want you to go from to the A address and go 2 in memory. So it'll go A here, this is A. It'll go +1, +2, and it will give you the value at this address. And so that's why if you go A2, you'd actually get given, like let's say there's 7 stored in here, you would get 7. This can also this is just the square bracket notation, because similarly, because you're actually just dealing with a memory address, and because A is the memory address, we can just say A plus 2. And if we dereference this, so this star sign would actually would get you what is at that address, this would also give us 7. So hopefully this doesn't confuse anyone. I also probably should have said more concretely that we have this star and the ampersand notation. Now the ampersand notation I used a couple of seconds ago, saying that when you use like ampersand of some variable, it will return you the address of that variable. And obviously if you have the address of a variable, you want to access what's at that address, and to access what is at that address, you dereference it using the ampersand. So if we have like integer foo equals 7, like this is at the top of our code, we can then have an integer pointer, we'll call it pfoo, and we would set that to the address of foo by using this ampersand dereference. But then if we want to modify what is pointed to by pfoo, we could then dereference pfoo and set it to like 8, right? And this would mean after this line of code has been run, foo here would actually be equal to 8, because what this line of code is doing is saying, I want you to go to the address stored in this register, in this variable, and set it to this. So because pfoo is storing a memory address of foo, what this does is it goes to the memory address of foo and it takes the variable there and then it sets it to 8. So in turn, it's setting foo to 8, if that makes sense. Okay, so now that we know hopefully like what the pointer does and the square bracket notation, whatever, it's all a bit confusing. This is why students and it's really hard to explain it as well. Then we have to understand when you use a pointer. And this is when you come into memory management and memory allocation. And so we sort of need to get into the context, which there's not a slide for it. But like when you have a function and you say at the top of your function, like you have some my func whatever, and you have some, and you return here. Now, if you create an integer here, integer a, this integer is created in memory on the function stack. When this function returns, this stack is essentially destroyed. There's no more references to this stack, and this variable becomes no longer valid. And so this is what I say by the scope of an integer or the scope of a variable is by saying where is it valid? The scope of a is inside of my func. While we're executing code from inside this function, a exists, but as soon as a function returns, the memory address still exists, but it's not being managed. And if you were to go and read somehow get a reference to that address, you can't guarantee what's the address, and there you would get undefined behavior. But we can allocate memory that is like outside of the scope of a function, let's say. And this is when you get into these sort of memory management functions such as malloc. And so malloc stands for like memory allocate, and what it's going to do is it's going to actually allocate a chunk of memory that is not tied to, for instance, the scope of a function. Once, like if we go into a function, we can access the memory safely, we can return from the function, we can still access the memory safely as long as the memory hasn't been freed. Now, free is the opposite. It sort of says, okay, this memory is no longer being managed, we don't have any variables there. And then after a free, if you were to access the same memory locations, you could have a problem again. But the idea is that we call this dynamic allocation, is that we're dynamically allocating chunks of memory for using in functions. And you have like static allocation, meaning that you actually you define the variables in your code, meaning like at the top of your like main.c, you might have int a equals 2, and because this variable existed when you compiled your code, it will actually get allocated before the code is run. And so this is why it's called static allocation, because it's allocated statically during compile time, whereas the actual memory addresses that get used for this malloc allocation are determined dynamically during runtime. And so this is why it's called dynamic memory allocation. So in embedded systems, static memory allocation is generally preferred because we can know at compile time how much memory or where this memory is getting allocated, but dynamic is a much more like complex beast to tame because it's happening during runtime, right? So hopefully this has made a bit of sense. So, oh yeah, exactly, great. He's actually said, so this decay is this here. So like a char, like the char array type decays into a char pointer. So we can use them the same interchangeably, but they're not explicitly the same, and you can get compiler warnings and stuff. But yeah, so now we'll sort of like skip this slide because it's not my figure and I don't want to have to deconstruct it. But when we compile a program, we get like the program's compiled into assembly and things. For instance, the static variable I was just mentioning, this has to exist somewhere in the memory like chunk that is our program. And so we have all different sorts of sections, and without going into like super detail of like how memory is mapped and structured and whatnot, you essentially have a few basic different sections. Like you have your text, and this is generally code, I believe. Initialized data and uninitialized data. And so this should make sense. Like if you have int a and then you have int b equals 2, obviously this guy is not initialized and this guy's initialized, and so they get split up into the different things. But these variables were defined in your code statically, and so they'll end up in these sections here. Now, if you had, for instance, there's also like read only. So if you had const int b equals 2, it would land in read only memory. And so this can't be written to because it's landing in read only memory, like physically read only memory usually. But then you also, for instance, have the heap and the stack. And so this heap and the stack is where memory is things are placed and used from during the execution of your program, right? So here we can see the stack this is sort of like the temporary, as most stacks, you sort of like you push to it and you pop from it, and this is the temporary memory essentially used when we're dealing with scopes. So when you go into a function, you're pushing things onto the stack, and when you return from the function, you start popping these things off of the stack. And so you can also kind of say function stack, but really what it is, it's usually just a chunk of memory on top of the stack that exists or that will get popped once the function returns. And so it's sort of like the function's chunk of stack. Exactly, and this is sort of outlined here. But then we get to the heap, and this is sort of like where you store this dynamically allocated stuff, which I was talking about here, like using malloc and whatnot. So malloc, like stuff allocated on the heap, is not directly connected with like a scope of like the scope, the function scope, because obviously when the function returns, the scope, like the stack kind of gets popped off, like the variables and whatnot gets popped off of the stack. But because this stuff is allocated in the heap, it still exists. And so this is where your variables will end up when they're getting allocated using malloc, calloc, realloc, whatever, right? And so as I was saying before, it's hard in real-time code because it's not very predictable. Usually you'll allocate your memory, like if you were to actually statically allocate your variables using at compile time, they would land in these sections here. And so therefore when you analyze the binary, you actually know like how big they are, where they are, and whatnot. So I think now I'll quickly, I'm hoping I've somewhat covered what this is, like in this little video, like how pointers work. I think the easiest way is to just do an example. So now I'm going to stop this one here and I'm going to open another one and I'll just do some basic coding exercises. So